All right, strap in, everyone. Today, we are going deep, and I mean deep, into a topic that's really pushing the boundaries of what we thought was possible with AI. It's called physics-informed deep learning.
It might sound like something out of science fiction, but we're basically talking about teaching computers to not just crunch numbers, but to actually understand the fundamental laws of physics.
Yeah, it's mind-bending stuff, and we're not just theorizing here. We're going to be unpacking a really groundbreaking research paper.
The paper's called Physics-Informed Deep Learning, Part 2, Data-Driven Discovery of Nonlinear Partial Differential Equations. A bit of a mouthful, I know.
Catchy title.
But the authors, Raci, Pertikaris, and Karniadakis, they've basically laid out a roadmap for how to use a special kind of neural network to uncover hidden equations, the kind that govern how the universe works, from just looking at real-world data.
Okay, so we're talking equations, but not your simple high school algebra kind of equations. We're in the big leagues now.
Exactly. We're talking about partial differential equations, or PDEs for short.
PDE sounds intimidating.
They might sound a bit intimidating, but they're actually the language of the universe. PDEs describe how things change and interact over time and space.
So give me some real-world examples. Where do we see these PDEs in action?
Oh, everywhere. Weather patterns, the way fluids move, like air over an airplane wing or blood flowing through your veins, how heat spreads through a material, the behavior of sound waves, the list goes on and on. Pretty much anything that changes in a continuous way can be described by a PDE.
So these equations are kind of a big deal. They underpin so much of what we see and experience in the world around us. But the problem is, it's traditionally been really tough to figure out the exact form of these equations just from observing things in the real world, right?
Yeah, it's like trying to figure out the rules of a game just by watching a few matches. You might get a general sense of how things work, but you wouldn't know the precise rules. And to make things even harder, in the real world, we rarely have perfect, complete data. It's often messy, incomplete, and full of noise.
Okay, so how do we deal with this messy reality? How do we uncover these hidden equations when the data is so imperfect?
That's where these special neural networks come in. They're called physics-informed neural networks, or PINs, and trust me, they are changing the game.
PINs. Sounds futuristic. So how do they work? What makes them different from your regular run-of-the-mill neural network?
Imagine you have a detective trying to solve a case, right?
Okay, I'm picturing it.
A traditional neural network is like a detective who's just looking for patterns in the evidence. They sift through the data trying to find connections and correlations, but they're not necessarily using any outside knowledge to guide their investigation.
Right. Just looking for patterns, brute force style.
Now imagine that same detective, but they also have a textbook on the laws of physics sitting on their desk. That's what a PIN is like. It's not just looking for patterns, it's actually using its knowledge of physics to guide its investigation.
So it's like the PNN has a built-in understanding of how the world works. It's not just blindly fitting the data, it's trying to understand the underlying physics driving that data.
Exactly, and that's what makes PNN so powerful, especially when you're dealing with limited or noisy data.
Hmm.
It's like being able to solve a jigsaw puzzle even when half the pieces are missing and the picture is all blurry.
Okay, I'm intrigued. So what did these researchers actually do with PNNs in this paper? Give me a real-world example. How did they put these things to the test?
Well, they started with something called Berger's equation. Maybe not a household name, but it's actually a pretty fundamental equation in fluid dynamics. It basically describes how waves form and interact.
Waves, like in the ocean.
Kind of, but it's more general than that. Berger's equation governs things like traffic flow, how shock waves propagate, even certain aspects of cosmology. It's a really versatile equation that pops up in a lot of unexpected places.
Okay, so this is an equation that has real-world relevance. I'm starting to see the bigger picture here. So what did the PNN discover about Berger's equation?
The researchers gave the PINN a set of data points that had been generated using Berger's equation. But here's the catch. They didn't tell the PINN what the equation itself actually was. They just gave it the output, the answers, so to speak.
So it's like they gave the PNN the answer key without the questions, and they wanted to see if the PNN could reverse engineer the equation just by studying the answers?
Precisely. It was like a test to see if the PNN could really understand the underlying physics, not just memorize patterns.
How did it do?
The results were amazing. The PNN was able to accurately identify Berger's equation using just 2,000 data points. 2,000. That's an incredibly small amount of data, especially for a complex system like fluid dynamics.
2,000 data points. I'm trying to wrap my head around that. That seems incredibly efficient. How does that compare to what a traditional deep learning model would need?
Oh, a traditional deep learning model would need orders of magnitude more data to even come close to that level of accuracy. We're
Yeah.
talking tens of thousands, maybe even hundreds of thousands of data points.
Wow, okay. So PNNs are incredibly data efficient. But what about noise? Real-world data is rarely clean and perfect. Did the researchers throw any curveballs at the PNN?
They did. They actually introduced noise into the data, up to 10% noise, which is a lot. But here's the thing. The PNN still nailed the equation. It wasn't fooled by the messiness.
So it's robust. That's a big deal because, let's face it, most of the data we collect in the real world is inherently noisy. There are always going to be measurement errors, environmental factors we can't control, all sorts of things that can muddy the waters.
And that's why this robustness is such a game changer. The fact that PNNs can handle noisy data so well really opens up a whole new world of possibilities for scientific discovery.
I'm officially impressed. But Berger's equation, while cool, it's still a relatively simple equation, right? Can these PNNs handle something more complex, something with real-world engineering applications?
Oh, absolutely. In fact, the researchers took on one of the most notoriously difficult problems in fluid dynamics. They decided to tackle the Navier-Stokes equations.
Okay, now we're talking. The Navier-Stokes equations, those are the ones that describe how fluids flow, right?
Exactly. They govern everything from the air flowing over an airplane wing to the blood pumping through our arteries. They're the bedrock of fluid dynamics.
But I've heard they're notoriously difficult to solve. What makes them such a challenge?
Well, for one thing, they're nonlinear, which basically means the math gets really messy really quickly.
Uh, Nonlinear equations. Always a headache.
And to make matters worse, in real-world situations, you're often dealing with complex geometries. Think about the curved surface of an airplane wing or the intricate network of blood vessels in the human body. It's not like you're dealing with nice, neat, straight lines and simple shapes.
So trying to solve these equations for those kinds of complex scenarios, that must be a computational nightmare.
It is. Traditional methods can do it, but they require enormous amounts of computing power and time. It's like trying to simulate the entire global weather system on your laptop.
Okay, so how did the researchers approach this problem with PNNs? Did they just throw the whole Navier-Stokes equation at it and hope for the best?
Not quite. They focused on a classic problem in fluid dynamics. Incompressible flow past a cylinder.
Incompressible flow past a cylinder. Paint me a picture. What does that even look like?
Imagine, for instance, wind flowing around a bridge pier, or water flowing around a rock in a stream. It seems like a pretty simple setup, right? But it actually leads to a really fascinating phenomenon called the Kármán vortex street.
The Kármán vortex street. That sounds almost poetic. What is it exactly?
It's a pattern of swirling vortices that form downstream of the cylinder. You've probably seen it in nature, those beautiful swirling patterns of clouds behind an island or the way smoke curls up from a chimney.
I see. So those mesmerizing swirling patterns, that's the Kármán vortex street in action.
Exactly. And it's not just a pretty pattern. It has real-world implications.
Like what?
Well, it affects things like the drag on objects in a fluid, the vibrations on structures, even the mixing of fluids. Understanding how these vortices form and behave is crucial for designing efficient airplanes, stable bridges, all sorts of things.
Okay, so they set the PIN loose on this vortex street problem. What kind of data did they feed it? Did they give it information about both the velocity and pressure of the fluid?
Here's where it gets really interesting. They only gave the PINN data about the velocity of the fluid at different points around the cylinder. They completely withheld any information about the pressure field.
Wait, hold on. They expected the PIN to figure out the pressure just from the velocity data. That seems impossible. Isn't pressure like a fundamental part of how fluids behave?
It is, but remember, the PIN isn't just blindly fitting data points. It's incorporating its knowledge of the Navier-Stokes equations into the learning process. It's using those equations to fill in the gaps, so to speak.
So it's like the PIN was able to deduce the pressure just from the velocity information and its understanding of how fluids behave according to the Navier-Stokes equations.
Exactly. It's like the PNN was able to say, okay, I know how fluids move, I know the velocity at these points, therefore the pressure must be this.
That's incredible. So what were the results? Was the PNN able to accurately predict the pressure field?
The results were stunning. The PNN accurately predicted not only the velocity field, which it was trained on, but also the entire pressure field around the cylinder, despite never having seen any pressure data during training.
That's mind-blowing. So we're not just talking about finding patterns in data here. These PNNs are demonstrating a level of understanding that's almost, Well, human-like. They're making inferences and predictions based on incomplete information, just like a scientist would.
It's a glimpse into the future of scientific modeling. Imagine being able to predict hidden variables in all sorts of complex systems, from climate models to financial markets, just by feeding limited data into a PNN.
Okay, the possibilities are starting to become clear and they are incredibly exciting. But before we get too carried away, let's talk about real-world data again. We know it's messy. Did the PNN stumble when they added noise to the velocity data?
Not at all. Just like with the Burgers equation experiment, the PNN performed admirably even when the data was contaminated with noise. It's like it was able to see through the noise and focus on the true underlying physics.
This robustness is really remarkable. It seems like a key feature of PNNs. But, all the examples we've discussed so far rely on having data that covers the entire time period of the phenomenon we're studying. What happens if we only have snapshots of the system at specific moments in time?
That's a great question. And it leads us to another exciting aspect of this research. They actually tackle the challenge of working with limited time data. You see, in many real-world scenarios, we don't have those nice continuous data sets that span an entire event.
Right, it's more like we're getting glimpses of the system at certain points in time, like snapshots.
Exactly. Imagine trying to understand a complex chemical reaction, but you only have readings from a few lab tests taken hours apart. Or trying to predict the path of a hurricane, but you only have satellite images from every few hours.
Okay, yeah, that makes sense. So how do you even begin to model something like that when you have those gaps in the data? It seems like you'd be missing crucial information about how the system is changing over time.
That's the ingenuity of what the researchers did. They developed what they call discrete time models.
Discrete time models. Kitschy.
These models are specifically designed to handle those situations where you only have data from a few points in time. In fact, they showed that these models can work even with something as sparse as just two snapshots taken at different times.
Two snapshots, seriously.
Yeah,
That just doesn't seem like enough information to understand a complex system. I mean,
Yeah.
how do you fill in all those gaps between the snapshots?
it does seem like a stretch, right? But that's where the power of physics comes in. Remember, we're not just throwing data at a black box and hoping for the best. We're leveraging our understanding of the fundamental laws of physics to guide the learning process.
Okay, so how do these discrete time PINNs actually work? What's the magic trick?
Well, they take advantage of something called run-CUDA methods.
Runge-Kutta methods, those ring a bell vaguely. Remind me.
They're basically a set of numerical methods that are really good at approximating solutions to differential equations. They work by breaking down the problem into a series of small steps.
So it's like they're creating a series of stepping stones to get from one snapshot to the next, using their knowledge of physics to guide each step.
That's a great way to think about it. And to really test these discrete time PINNs, they went back to that trusty Burgers equation. Remember how well the continuous time PIN did with identifying the equation using 2,000 data points across the whole time span?
Yeah, that was pretty impressive.
We'll get this. The discrete time PINN, using just two snapshots taken far apart in time, was still able to accurately identify Burgers' equation.
No way! Two snapshots! That's incredible. So even with incredibly sparse data, these PNNs were still able to extract the underlying physics.
It really highlights the power of combining deep learning with these clever numerical methods and a good understanding of physics. But they didn't stop at Burgers' equation. They wanted to push things even further, so they decided to tackle the Korteweg-de Vries equation, or KdV for short.
KDV, now that one I'm not familiar with at all.
It's a bit more specialized, but it has applications in a lot of different fields. It basically describes the behavior of waves in shallow water. You know, like when you throw a pebble in a pond and those ripples spread out?
Yeah, I can picture it.
That's the kind of wave behavior that KdV governs. But it also pops up in other areas, like acoustics, nonlinear optics, even plasma physics.
Okay, so it's a multi-talented equation. But why was it a good challenge for these discrete time PINNs?
Well, because it's significantly more complex than Burgers' equation. The math is a lot trickier, and the wave patterns it describes can get really wild and unpredictable.
Sounds like a tough nut to crack. So they essentially gave the discrete time PINN two snapshots of these crazy wave patterns and said, good luck.
Pretty much. And you know what? The PINN rose to the challenge. Despite having only two snapshots to work with, it was able to accurately identify the parameters of the KdD equation and capture those complicated wave dynamics.
That's pretty amazing. It really feels like we're witnessing a paradigm shift in scientific modeling. We're moving away from this dependence on huge data sets towards a more nuanced, intuitive way of extracting meaning from even tiny bits of information.
It's an incredibly exciting time to be working in this field. And to think we're only just scratching the surface of what's possible with PINs. Who knows what other mysteries of the universe these things will help us unravel in the years to come.
It's really mind-blowing stuff. Thanks for taking us on this incredible journey into the world of physics-informed deep learning. I have a feeling this is just the beginning of a very exciting chapter in scientific discovery.
My pleasure. It's always a joy to share the wonders of science with a curious audience.
And to all our listeners out there, keep exploring, keep asking questions, and keep that curiosity burning bright. Who knows what incredible discoveries await us in the uncharted territories of science?